Okay, welcome back, everybody. We're going to do some computations involving witness sets today. Before we do so, I want to just summarize the last lecture on this board over here, and then tell you a fact over here called the trace test. So the takeaway from the last lecture, and this especially applies to if you don't really care too much about the proofs of everything and you're willing to put a lot of this on faith. You should be convinced at this point that you can compute witness sets of the m-dimensional reduced parts of a variety cut out by n minus m equations using homotopy continuation. So you can think about that in terms of parameter homotopies, where the parameter space is the space of linear spaces that you would use to cook up a witness set. And the algorithm that we ended in the last class in is called the monodromy breakup algorithm. And it tells you that by using monodromy, you can bust up this witness set for lots of components into witness sets for each of the components, right? So in particular, you can identify the components, at least in dimension m, of a variety cut out by n minus m things. And you can do this effectively on a computer. And indeed, we will do this today on a computer. The other thing I want to tell you is new. So this is called the trace test. And honestly, this is a bit of a miracle until you prove it yourself. I really encourage you to prove it yourself for just plain curves. And you're going to have a great time doing so when you reach the end. We won't be proving it in class, but I'll say the statement. So you have some irreducible variety. Here's one. And you have some generic linear space of complementary dimension. Here's one. But you think about this linear space of complementary dimension in a family of them. Okay, so I want you to imagine again this line being swept through the variety in either direction. So you're in a parallel family of linear spaces. Parallel, by definition, doesn't intersect in C to the end. Okay. Okie doke. Now, these witness points here, oh, and I'm going to think about this as L naught. And the family is L t. Right, so T is going up, you go this way. T is going back, you go that way. Okay, cool. The trace of this collection of points is the coordinate-wise sum. Okay, so each of these points has coordinates. You can compute them using homotopy continuation. And now you just add up all those vectors together. You'll get some other vector that's way off the blackboard. And that's called the trace. Some people, like me, who like to draw pictures, define the trace to be the average, the coordinate-wise average of all these points. Because then I can say, yeah, the center of mass of these 4 points is probably maybe around here. Yeah? That's just the coordinate-wise average. You do the sum and then you divide by the number of points. And indeed, as this movie scans through, with t being time, you can compute the trace the whole time. And that will, a priori, maybe be a curve. Right? So at every t value, you choose the average. And you just track that center of mass. Importantly, you can do this even if you don't know whether or not you found all the points. Okay, so that's no longer my trace here. So here we have T naught, which is just these 3 out of the 4 points. So it's some subset of the witness points. Okay. And I can look at the trace of these. So the center of mass is around there. So this is trace of T naught. And again, I can look at how this curve moves. Right? And this theorem states that the behavior of this trace curve differs wildly depending on whether or not you have all the points or if you only have a subset of points. If you have all of the points and you're computing the true trace of a linear section of an irreducible curve, so like that was really the actual average, that trace will be a line. this is the trace of S of t. Miracle, okay? Absolute miracle. Not only does it say that you'll get a line if you have all the points, it says that you will not get a line if you don't have all the points. And now I will share my screen and we'll demonstrate this. All right, here's GeoGebra. X cubed minus y cubed plus x times y equals 0. Yeah, that's good enough. So here's a variety. It's a nice little cubic, no grid, no axes. There we go. Okay, great. All right. Prajwal, give me a number. 10. Jacob, give me a number. 5. So we're gonna need a little scroller called T, and then we're gonna look at, oops. 10 times x plus 5 times y plus t equals 0. Boom, there we go. Okay, cool. Sure, that'll work. No, cancel. You. Don't want this line. Okay. So now, great. So now I got my family of lines. Beep, 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 beep. Yeah, very good. Let's get some colors. So that makes my brain happy. Awesome. Okay, cool. Let's intersect these. It's just a cubic and a line. GeoGebra should be able to do it just fine. We got A, B, and C here. A plus B plus C divided by 3 is my trace. That is D. Okay, I do not care about seeing A, B, and C right now, but I do care about seeing D. You're going to be a big old hollow circle, which is orange. Great. Okay, so now the trace test says that as I wiggle T back and forth, this orange dot will carve out a line. So I can actually make GeoGebra kind of save the positions. Whoa. Okay, like raise your hand if you knew about this theorem. This is crazy, right? There's no reason why you would think that. All right, and what's happening when this orange thing disappears? We're getting a tangent line. So we're on this exceptional set of the branched cover. And so we can change the number of real solutions. And indeed, GeoGebra is only doing things over the reals. So it is not looking at these complex conjugate points. Okay, but let's think about what happens to the trace when we're dealing with conjugate solutions. The imaginary parts cancel out. So the trace is still real here, right? Like, so it really is this real line. Okay. So far, so good? Okay. But that's only half of the trace test. So far, the trace test that we've seen right now is that if you have all the points in a witness set, the coordinate-wise average moves linearly as you move this linear space in a parallel family. The other part of the trace test says that if you don't have all of them, you will not get a linear trace. All right, so maybe we only computed A and B. And so now our average is A plus B divided by 2. Okay, so nobody knew about C. Nobody's computing D anymore. Let's reset our picture. We only have these two. Okay. Again, this is totally going to happen on a computer when you can't visualize the system you're solving. You're in 20 variables. You have 100 parameters. You have no idea whether or not you have all the points. You want to figure it out in some like rigorous, semi-rigorous way at least. Okay, so here's E. Okay, let's stick the trace on. You are not moving in a line. Okay. Okay, questions. So we have now demonstrated the trace test, and you should feel a little shocked, maybe. I don't know. I love this thing. It is the same theorem as the first elementary symmetric polynomial is linear. Okay. Great. Okay, I will say a little bit more while we're doing computations about exactly how we're going to use that in numerical algebraic geometry. For now, I want to not mirror the displays because I do have some notes on the computation today. Great. Keep changes. Thank you. Let me throw this over here. Okay, and let me share desktop 2 here. There you go. Okay, great. So you got desktop 2 over there. Yes. So I need to go into all right, cool. So let's pull up a Julia terminal here. Let me share my screen. Oh no, I am sharing my screen. Great. Let's pull that up. Oh. Let's go ahead and throw this bar upstairs. All right. So I'm going to pull some of our monodromy story from last time here. So random loop. So you input some base point. Yeah, let's just do triangles. So we need another parameter. That's the same size as the base parameter. And then we gotta end the loop by completing the triangle by putting the base back. Boom. Okay, let's get a polynomial system we care about. How about let's take have to be the witness system for my favorite circle and a degree 6 polynomial. Okay, so that's what I want. The variables are x and y. My parameters are a, b, and c. And I'll get an error because I didn't define these variables or parameters, okay? But that's okay because Julia has memory. I just go up, up, enter, and I'm good to go. And now I have this is the witness. This is the square parameterized polynomial system corresponding to the witness cover, okay? So yeah, however scary WX looks like, that should look less scary, okay? Awesome, great. So let's do random complex F643, and let's do S is gonna be like solve F, please, with target parameters E. Okay. How many solutions do we expect? What was their system? 12 solutions, we think? Are we mixing up multiplication and addition, perhaps?
2 and 6. 6 to the 12.
Yeah, so 6 plus 2.
6 plus 8.
Awesome. Good. Great. Okay. I was trying to buy some time there. Okie doke. And how about monodromy group? What do we expect this monodromy group to be? As the ABCs move around, I'm moving a line around. This is definitely the union of 2 plane curves. So this should be S2 cross S6, unless I picked a degree 6 polynomial that's reducible.
We don't know that.
We don't know that yet. Hey, awesome. Ooh, what would happen if I did monodromy solve? So what does monodromy solve do? Well, it finds a random point in a random fiber, and then it does loops to try to populate. But our theorem that we saw today says you're not going to be able to reach every solution. You're only going to be able to reach the solutions that are on the component of the witness cover that you started on, which is either going to be an orbit of size 2 or an orbit of size 6. So let's see that in action. I should have clicked this before I exposited. So we're either going to get 2 or 6. Any guesses of which? And take bets. 6. Nice. Wow, great. Oh, there's some 2s. 2 or 6. But no promise as to which. Okay. All right. So what's this tell you? You have your favorite parameterized polynomial system. You didn't think of theory at all. You're like, I'm going to throw this into Julia and use monodromy solve. I found 6 solutions, so there must be generically 6. No. No, 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 no. You need to know that the variety upstairs is irreducible. Do not make this mistake. Okay? And that's fine. Like, when in doubt, just do it the painful way and construct a big old Bezier start system. That'll get you everything. Okay? You only get to do monodromy when you know you're irreducible upstairs. Okay. Okie doke, let's continue. All right. So last time we had this function called tracks solutions around loop. It was good naming. It took the parameterized polynomial system, a set of current solutions, and a loop, and it just took the current solutions and moved it along the parameters in loop. So this is how that loop works. Okay. Okay, so SP. The syntax for this was F current sols and loop. So I could track the solutions around a loop of F of my current solutions and a random loop around P. Okay. And of course, this is gobbledygook. I can't parse this. Great. Yeah, I had 8 solutions. They looked ugly. I threw them around a loop. Still ugly, but ugly in a different permutation. Okay. So let's write a function that can parse this a little bit better. Okay. Great. What do we need to do? Okay, so somebody's going to give us 2 lists of numerical vectors. And we got to figure out what permutation happened, right? So we will have S and then the base S. So base S is how it started, S is how it went. Okay. And let's throw in a tolerance numerical. So this is a great function. It's called find first. So I'm going to have some function here. X goes to something. I'm going to find the first thing in this list, base S, such that this function evaluates to true. Okay, so X will go to X minus S. So this is going to give me the first X in base S, which equals S. I want to do that for S. So for each solution in my base, I'm going to look at the new stuff and find which number in my list is that solution. So think about how this list is computed. So first thing we do is we take the first solution in our base fiber. Okay, we call that solution 1. Okay. And now we look at the solutions we computed via a loop. And we go, which index is this one sitting in? Right? Which index is our first solution sitting in? And that's what this is doing. And it's then doing that for each. Okay. So it's actually a 1-line thing we got going on here. Okay. So here's our S. Yeah, let's make S equal to solutions of S. Okay. Okay. And now I want to call this new S. This is tracking the solutions around a loop. And now I want the numerical permutation new S. This is not a function. which evaluates to a Boolean, but this one is. Okay. So I didn't want to just compute the norm. I wanted to compute how close these were up to some tolerance. Okay, let's try again. Yay! Okay, so 1 stayed at 1, 2 stayed at 2, 3 stayed at 3, 4 went to 5, 5 went to 4, 6 went to 6, 7 went to 7, 8 went to 8. Awesome.
So when will we to
That's a transposition. I don't know. It's just a transposition. It could have been 2 points in the degree 6 component that moved around. I don't know. Okay. So let's pull up Oscar because, man, I'm not doing any of these group theoretic computations by hand. Heck no. Even in S8. And so, yeah, Oscar is lovely, but it takes a little while to load, especially if you're on Zoom. So we just relax. Okay, so what's going to happen? So I have this way of cooking up new solution sets, which are maybe permuted by just shooting things over random loops. And I have a way to convert that data into one-line notation for a permutation. Okay, so I can do that like 100 times, right? And then I can ask Oscar to tell me what group got generated. I can ask it to describe it to me. It'll do its best to like give a human readable description. I can ask for the orbits, right? And I will ask for the orbits. Because that will tell me which points go together in the witness set. Okay, so we're going to compute 100 loop. 100? I don't know. It's a little. Let's do 10. My new source. Yay, 10 permutations. That's a subgroup generated by the permutations. There it is. Please describe it to me. S2 cross S6. Cyclic group of order 2 is the same thing as symmetric group of order 2. Okay. 3 and 7 go together. 1, 2, 6, 8, 4, 5 go together. Ta-da! Everything I said was true. Okay? Okay. Any questions? That is the monodromy breakup algorithm. All right, let's do some trace test stuff. So trace is already a function in homotopy continuation.jl, but it uses the actual witness set data structure, which we are avoiding for pedagogical reasons right now. So the trace of a bunch of points is just going to be the sum of them. Okay, coordinate-wise sum. Function. My trace test. What do I need? I need F. I want an S. I want a P. Okay, so S is a solution set that I hope passes the trace test as I move around. P is my base parameter. And great. Yeah. So how do I get a parallel family of lines? I just move the constant term, right? So I'm just like, I can add 1 to the last parameter, for example. So V is a vector, which is going to be the direction in which I move in my parameter space ABC. Yeah, so I want the vector 0, 0, 1 for ABC. That will move the constant term. right? Because A is the coefficient of X in the linear form, B is the coefficient of Y in the linear form, and C is the constant term. So I want nothing times a vector of length of P minus 1. And that's my dumb way of doing it. Probably zeros of that length would have done the trick. And then I just want to throw a 1 at the end. Okay. My first parameter will be the parameter I started, and my first solution set will be my first solution set. My second parameter will be the parameter I started in, plus 1 step in the constant direction. Okay. So that's just another parallel slice. Okay. And then S2 will have to be, well, I'll have to solve it. Start parameters is P, target parameters is P2. Beep, boop. Great. P3 will be P plus 2B. S3 will be solutions. Okay. So now what's the story here? I got 3 slices. Okay. So object properties, increments 1. Okay, I want very discrete movements of my T now. Okay. So I got like T1, T2, T3. So these are the 3 things I have going on. Okay, and how do I check if those 3 traces lie on a line? Well, the one in the middle better be the average of the 2 on the end, right? That's the trick. Okay. So what do I want? I want the trace of S1 plus, sorry. So I'm going to take the average, equivalently the sum, of the first and third solution sets. Subtract off 2 of the middle one. Okay. So this is going to be some vector, which if the trace test passes, this should be a vector of zeros. Because that's the same thing as saying the average of the trace of the first thing and the third thing is the trace of the second thing. And that's the same thing as saying they lie on a line. Okay. Let's check out those orbits again. And there's our S. Okay. So we got the orbits. So 1, 2, 6, 8, 4, 5 are on a component. 3 and 7 are on a component. So let's do the my trace test. Let's do the whole thing. Great. That is 0 numerically. Okay. And that is telling me that the point set I have is a union of witness set point sets for irreducible components, right? Trace test only says stuff about irreducible stuff, right? And indeed, if taking the trace with 3 and 7 is linear and taking the trace with 1, 2, 6, 8, 4, 5 is linear, then the sum of those linear form functions is a linear one again. So the trace, if I include all the solutions, will be linear. Okay. So now let's do it when I only use, let's say, the first and the second and the third points. Okay. So according to this orbit calculation, 1, 2, and 3 do not all live on the same irreducible component. In particular, 1, 2, and 3 is not a union of witness point sets for irreducible components. So we should not be getting a linear function out. So this trace test that we wrote up should be giving us a vector that's very much not 0. And it's very much not 0. Okay, well, what about just 3 and 7? That should be 0. Yeah. And then similarly, 1, 2, 6, 8, 4, 5. Okay. Anything else really won't be. Okay. This is how you verify that you have a complete set of witness points. Any questions? Okay, then I want you to listen carefully to this statement. This is a good stopping criterion for a monodromy solving algorithm. Okay, so how did monodromy solving work? In the context of witness sets, I would have 1 point in a witness set for an irreducible variety, and I would move that linear space around and I might find another. Okay, now I got 2 points. And I use Kate and Alex's idea and I shoot both of those around. And maybe I get 4 points, maybe I get 3 points. You know, I keep on finding more and more points. But the way I gave you that algorithm is I said you should stop after like not making any progress for like 5 loops. However, now you know you can stop when the trace test passes. The trace test gives you a stopping criterion for the monodromy solving algorithm. Okay. And now I will offer one more insight. Let's say you hate monodromy. Okay, you never want to do monodromy, ever, 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 ever. But you love the trace test. Okay. And you did your computation and you found a point set S with 8 solutions. How can you figure out how to partition those into those that are on irreducible components? Right? How can I find the orbits without doing monodromy? I could take every possible subset of those 8 points and see which ones pass the trace test. The minimal such subsets will be witness point sets for the irreducible components. Okay. The problem is that you don't want to go through 2 to the 8 many subsets. And even worse, when you're doing things in like the real world, which means either real world applications or real world pure mathematics, right? Because this applies to both. You don't just have 8 solutions. You have hundreds, thousands, hundreds of thousands, and you're not doing 2 to the 100,000 many combinations to try to find the correct way to partition up this huge solution set, right? You suffer a so-called combinatorial blowup in that algorithm, but monodromy fixes this for you. Okay. Great. Any questions?
Is there a minimum number of points to check in order to conclude reasonably that okay, this collection of solutions passes the trace test?
You mean like I think I don't. You said a minimal number of points. So where is the minimal number of points? You mean like
instead of
2?
computing 2 power 8, is there a minimal way?
Oh, so doing this combinatorially via the trace test. So doing a decomposition combinatorially via the trace test.
Like for instance, instead of just checking all 2 power 8 pairs, is there a way of reducing that?
Oh, sure. Well, there's some obvious ones, I guess. You don't have to check the whole set. And you don't have to check the empty set. Assuming that you've really found a complete fiber in this witness cover. And then you only have to check half of them. Right? Because if some subset S passes the trace test, then its complement will too. Because it'll be like, because the whole thing passes the trace test because you found out everything. So that trace is linear. This trace is linear. But this trace is this trace plus this trace. So to conclude the complement passes the trace test, it's just a linear function minus a linear function is a linear function. Other than that, no, I don't think so. I mean, you might be working with a problem where you know some extra information. You might know that you have a degree 100 variety, which is the union of 5 degree 20 varieties. Okay, then you only have to check the 20 subsets. So the subsets of 100 things with 20 elements. Okay, does that help? I don't know. It's still pretty bad.
Notice knowing the degrees of the complements helps.
Yeah, but only it helps so much
But isn't
where
that-
instead of doing 2 to the n, you're doing n choose k, which is still pretty bad. Right? 100 choose 20 is bad still. You really don't want to do it this way. Unless you're in a really small situation.
So empty set, there's a real set. If a set is there, its complement is there.
I think that's
all.
That's it for free. Okay. This is a stopping criterion for the monodromy solving algorithm. When you're doing monodromy solving over a witness branch cover. A natural question you might be thinking is there a stopping criterion like the trace test for other famous covers? Right? So for example, let's say I'm solving a sparse polynomial system. Right? So this is not a branched cover. Sorry, it's not a witness branch cover. So you might ask, okay, is there a way to tell when monodromy solving is done and can stop? Right? And so that is current research. Okay. Yeah, so one thing you could do, if you're interested in working in this area, is you could find your favorite family of branch covers that come from algebraic geometry or applications, and try to construct a trace test somehow for that situation. Right? So maybe you're doing some enumerative problem in Schubert calculus. Maybe you're solving some interpolation problem. You're computing lines on a cubic surface, right? How do you know when you found them all? Without knowing a priori that the number is 27. So that's active area research. I think it's really interesting. And yeah, happy to chat more about that if you have questions. So I think that's all for today. And yeah, so I will stop the recording and take questions. Thanks.